Hello everyone, welcome to a new video of Dr. Cat Can Code. In this video, I'm going to talk about iterative improvement strategies in data structure and algorithms. This is a very useful knowledge for software engineer during their job interview as well as during their career. If you stick around until the end of the video, I will show you 3 practical examples demonstrating the idea of iterative improvement strategies. For those of you who don't know me, I'm Dr. Han Phan. I have been teaching for more than 10 years at multiple top-tier universities. I have also been programming for more than 20 years. I love programming and sharing my knowledge to the community. Please make sure to like the video and subscribe to the channel to make it easier for you to see the next useful video from me. Thank you. First, let's have a look at the definition of iterative improvement strategies. The idea of iterative improvement strategy is that it solves problems by making incremental changes or refinements to a solution in multiple iterations until the desired outcome is achieved or the problem is completely solved. So the key points here that you need to remember is that you start with some sort of arbitrary guess, and then you make incremental changes to the guess iteratively and improve it over time until you meet some certain threshold to say that, okay, I will stop here, no more iteration, and I will use this result. So what are the pros and cons of iterative improvement strategies? The 2 main pros are simple to understand and implement. You know, the idea is simple. You start with something and then you iterative improve it over time. It's efficient when an exhaustive search is impractical. It's not always possible to exhaustively cover all the situation in all sort of problems. Sometimes you need the timely return of the result. Then an efficient strategy using iterative improvement is very important. So what are the cons of this strategy? First one, we have no warranty of the global optimization. If the problem requires the absolute correctness, definitely iterative improvement might not be the first choice. Also, when you iteratively improve or increment or make some changes, sometimes there's no improvement to what the conversions of the result. Sometimes it improves, sometimes it decreases. And then the more iteration you run, the more variation of the result you have, and there's no warranty of the result of the outcome to converge. Okay, let's jump right into the first example. Thanks for watching until this moment. If you haven't, please like and subscribe to the channel. That's really important for me to keep going. Also make it easier for you to see the next useful video from me. Thank you. Okay, so let's look at the first example here. Square root. To calculate the square root approximation of a number, we start with an initial guess, then iteratively improve it using the Newton-Raphson formula until the difference between the new value and the last value is less than the tolerance. So we set up some sort of tolerance threshold so that we decide we don't need any more accuracy from this. So the Newton-Raphson formula allow you to make the new guess as an improvement, as an incremental improvement compared to the previous guess using the following formula: xn plus 1 equal to half of xn plus the initial number divided by xn. So that's how you calculate the next guess based on the current guess. Okay, so this is the Python implementation of that algorithms. So you have the input number. The initial guess can be an arbitrary number, say 1, because it's going to be changed anyway. Tolerance is how accurate you want your result gonna be. So if the result improvement is no longer greater than or equal to the tolerance, we can just stop, and no need to be more accurate than this. The maximum number of iteration also another stopping condition. Sometimes, because like I mentioned before, sometimes the iterative improvement strategy doesn't result in a converged algorithm. So definitely you need to stop your loop in some way, and the maximum number of iteration is a good way to achieve that. So you just look through the number of iteration and then keep changing, incrementally changing the next guess so that it will be closer to the actual square root. If it converge, it means the changes is less than the tolerance, and the changes is no longer significant, the improvement is no longer significant, and you just return the result. Otherwise, if this never run, it means we can't find anything that has better accuracy than this, but the maximum number of iteration has been met, so we also need to return the outcome. Okay. So over here we have just an example showing that square root of 25 is 5 using the Newton-Raphson formula and the iterative improvement strategies. Okay, so let's jump right into the second example. So for this second example, we will look at the calculation of the Euler number. The Euler number E is a mathematical constant that is equal to 2.71A2A, etc. Which can also be calculated as the sum of this infinite series, 1 plus 1 divided by 1 factorial, plus 1 divided by 2 factorial, so on and so forth. You can see that there's an incremental chance, there's an incremental change here that gives us a chance to apply iterative improvement, because you can see the next term is actually the previous term divided by 3. And this term is basically the previous term divided by 4. So this is a good chance for us to write a while loop to iteratively calculate the next term based on the current term. So the iterative improvement strategy here in this example involves computing the series iteratively by adding more terms to the sum until a desired level of accuracy is achieved. Okay, so start with some initial value, which is 1 here, and then the term we have is 1 and equal to 1. So this is our initial E and our initial term, and then our initial N is 1. From here, I can calculate the next term. The next term is 1 divided by 2, right? 1 divided by 2, and then just keep going. And then I also calculate the accuracy. If the term is less than the accuracy, I no longer want to add that term anymore or any further terms, because it's too small already, and it's much smaller than my required accuracy. So I can stop the while loop condition here when the term is no longer greater than accuracy, then I will stop the while loop. Okay. Yep. So this is just a demonstration of using the function. Okay, the final example. Thank you for sticking around, everyone. This example is very interesting because it related to a very important strategy in data science and AI, hue clumping. So a lot of problems in AI and machine learning involve optimization, finding some sort of local optimum of a fitness landscape. We start with an arbitrary solution, then repeatedly making small changes to the solution to see if the change result in an improvement. And the algorithm will stop when it reaches the local optimum. It can't find any better solution in the immediate vicinity. So as you can see here, this algorithm hill climbing doesn't warranty global optimal because the whole strategy involves around climbing up a small hill until you cannot find any better way to move backward or forward. So you stuck in the top of your little hill, which is local optimum. It's not a global one because there may be some other hills nearby that you cannot see anymore because you cannot escape. There's no better solution in the immediate vicinity, so you cannot escape your little local optimum. Okay, so I demonstrate the hill climbing strategy using this particular function minus x square. So this function and the objective is I want to find the maximum of this function. Obviously, this only local maximum because it really depending on where my initial starting guess is. It will find a local optimum within that vicinity only. So we have step size, the initial value, and the maximum number iteration. Again, I want to stop making changes after some maximum of number of iteration is met. And then within the range of max iteration, I will try to, for each iteration, I will try to calculate delta as a random value. I want to either move left or move right with a small amount of delta. And then I will check whether if I have made any improvement. I have made any improvement after I make the small step delta x, and then I calculate delta f to see if I make any improvement. So if I make some improvement, then I will update the value of x. So it means I will start walking to the next step in my hill climbing algorithm. If it doesn't, I will stay still and I will keep looping through that. And at some point, I might just keep staying still forever. So that's why, because I don't have any better solution outside of my immediate vicinity. So I will need to have this max iteration to stop the algorithm. All right. Thank you very much for watching, everyone. I hope you learned something. This is a very important knowledge for your job interview as well as for your software engineering career. Thank you very much again for liking and subscribing to the channel to make it easier for you to see the next video from me. That's it for me today. Thank you very much again. Take care. See you in the next video. Goodbye.